Welcome to this video on electric forces. We played a lot with the Van de Graaff generator last class, talked a little bit about charging, and this video is going to be a further explanation of a few things. So first, we're going to talk about the so-called first law of electrostatics and discuss this idea of charging by contact and charging by induction. You're going to learn what Coulomb's law is, that's how you pronounce that word, Coulomb's law, and you're going to figure out how to apply it to some problems involving electric forces. And we will define the electron, the Coulomb and microcoulomb, as different units of electric charge, useful in different situations. So if we talk about electric charge, if we were to take a fur, and this could be a synthetic fur, real fur, it used to be all real fur, and rub it against a rod made of rubber, because the rubber is typically not going to lose its electrons very easily, because rubber is an insulator, that's a word that we talked about last time, the fur will in fact give up its electrons as a result of this back and forth motion, and the fur will deposit electrons on the rod. The fur will more easily give up its electrons than the rubber will, because rubber is a better insulator than fur is. The result is that electrons move from the fur to the rubber rod, and now we have a positively charged fur and a negatively charged rod. We call the rod negatively charged because it has an excess of electrons, and we call the fur positively charged because it has a deficiency of electron, or it has more protons than it does electrons. In a similar setup, if we take a glass rod and we rub it against silk, we have electrons being removed from the glass and deposited on the silk, because silk, it turns out, is a better insulator than glass is. So the electrons are moving from the glass to the silk rod. Our silk ends up negative, and our glass rod here ends up positive. Again, we say that the glass is said to be positively charged because it has a deficiency of electrons, and the silk is negatively charged because it has an excess of electrons. So this is studied typically with something that we call an electroscope. And there are two main types of electroscope. We have a pith ball electroscope, whereby we would have two electrically conductive pith balls, they're called, or not, I guess they don't necessarily have to be electrically conductive. They usually are. They are just little metal balls that are hanging here. And we also have the gold leaf electroscope, where instead of having two spheres here, we instead have two little leaves of gold. They are gold or some other similarly conductive metal that are isolated inside of this chamber right here. So by using this idea of the pith ball, we can charge the rubber rod by rubbing it against the fur. We are going to negatively charge it. We can then transfer those electrons from the rod to each pith ball by actually touching the electron, or touching the rod to each pith ball. And then we will see that these two negatively charged objects, because each pith ball now has some negative electrons from the rubber, these two negatively charged objects will repel each other. We can do the same thing with the other rod. If we take the glass rod, remember the glass rod was able to be positively charged when we rubbed the silk against it. So we touch the pith balls with the glass rod here. The free electrons on the ball moves to fill the vacancies in the cloth. So those electrons looked for a location where there were less electrons in terms of the density of electrons. And right, this rod has a deficiency of electrons, so there's a whole bunch of places that those electrons can go to, which means that now the rod is less negatively charged, or perhaps even neutrally charged, and our pith balls are now positively charged because they have lost those electrons. So the positive charges then repel each other. If we were to then take each of those different rods, the glass rod and the rubber rod, and we were to charge two different pith balls, one with the glass, one with the rubber, we would see that there would be a force of attraction. The negatively charged green ball is attracted to the positively charged red ball, and so we have this idea that we have seen before of opposite charges attracting. And so this leads us to the so-called first law of electrostatics, which we talked about last class. Like charges repel, and unlike charges attract. So if we have negative charges, they repel. If we have positive charges, they repel. And if we have one positive and one negative, regardless of the position that they're in, they will attract. And so we can charge in a number of different ways. We talked about charging by contact last time. So if we take this uncharged electroscope and we charge it by touching the negatively charged rod to the top of the electroscope now is conducting that electricity, and it is taking these excess electrons up here and conducting them to get as far away from the electrons up here as they possibly can. So they get pushed down here because electrons are trying to get away from each other. And the result is that we now have a negatively charged electroscope, which will have leaves on the bottom that are sprayed apart, or splayed apart rather. So when the rod is removed there, we have pushed those excess electrons off of the rod. They're now in the electroscope, and now those two parts of the leaf move away from each other. Similarly, we can do the same thing with the positive charges. We take the glass rod. Those electrons that are inside of the electroscope here will move up toward the glass rod, which leaves the electroscope with a positive charge, and those bottom pieces will push apart from each other. So you should be really seeing here that, again, we are having only electrons move. Just the electrons are moving. The protons are not moving. The protons are much more massive. They're much harder to get. The electrons are what's moving. So even when we have a positively charged object, this positive charge is not pushing other when we had, a positively charged object, this positive charge is not pushing other positives away. What it's going to do is it's going to attract the negatives here. And those negatives will then fill in the gaps and leave a net positive charge over here. And so we can also charge by induction. And if you remember, induction was what I did when I took my finger or some other uncharged object and I brought it close to the Van de Graaff machine. The Van de Graaff machine, the hairs on the Van de Graaff machine, or rather the threads on the Van de Graaff machine, were attracted to my finger. And I said the reason that was happening was the electrons were pushing my electrons away. And as a result, the tip of my finger was positively charged. When my positively charged tip of my finger came close to the negatively charged thread, then they attracted each other. So we can do that by spheres. If we have two uncharged spheres and we bring close to those uncharged spheres this negatively charged object, we could do it with the negative or the positive, but this particular example does it with the negative. All of these electrons in the blue sphere are pushed away into the white sphere. These are in contact with each other. So the blue sphere now is positively charged, the white sphere now is negatively charged, and then we remove them, we separate them, we isolate those spheres, we move them apart from each other, keeping this negatively charged object here, right? And then we take away the rod, and now we have a net positively charged sphere on the left, the blue one, and a net negatively charged sphere on the right, the white one. Positive and negative. We didn't actually have any excess charge between these two. The total sum of the charges here in between these two spheres is still 0, right? That's represented by the 4 pluses here and the 4 minuses here. But what happened? We separated those charges, we isolated the spheres, and now we have two different charged objects. Think about for a second what would happen if instead of isolating them first, we just removed this rod. It's a very good question to know the answer to. We can also have this idea of induction for a single sphere where we have a polarization of the charge inside of the sphere. So we bring this negatively charged object close to it, it separates the charge into two halves of the sphere, right, two hemispheres, and the result is that now we have part of the sphere that's negatively charged, part of the sphere that is positively charged. And what can we do with that? Well, we can apply a ground circuit which allows those electrons to move to the ground so we can touch the sphere. And then the result is that we have a net positively charged sphere that was charged by induction. It was charged by induction because we rearranged those electrons inside of there simply by induction. You might think that this is charging by contact, but remember, by touching the sphere, we weren't imparting any new electrical charge to it. We were just allowing those excess electrons to move off. So we have kind of a charging by induction coupled with a charging by contact. And so to understand this idea of charge a little bit more, we have to understand this idea of quantity of charge. And we can define the quantity of charge by the number of electrons, but that's not terribly helpful because other things have charge, right? Protons have charge. So we have this unit that we call the Coulomb, C-O-U-L-O-M-B. And the idea is that it was discovered that electrons had certain amounts of charge associated with them, specifically by a gentleman named Millikan. And it was determined then that the unit Coulomb was made up of a certain number of electrons. So the Coulomb was the unit that was made up first, and the Coulomb was determined to be made up of a certain number of electrons. And here's how we define it. The Coulomb is the amount of charge that is incorporated, or that exists, in that many electrons. 6.25 times 10 to the 18th electrons. That's a ton of electrons. That's more than a billion. That's a billion electrons, right? 10 to the 18th electrons. So 6.25 times 10 to the 18th electrons, that's the number of electrons that are existing in 1 Coulomb of charge. Which means that for an individual electron, we have a very small amount of charge per individual electron. 1.6 times 10 to the negative 19th coulombs. Now we put the negative sign here because we do have two varieties of charge, quote unquote, two flavors of charge, negative and the positive. So the electron's charge, the charge of one electron, is negative 1.6 times 10 to the negative 19th coulombs. Now this unit of Coulomb is quite large. If we take a look at the number of electrons required for 1 Coulomb, that is ridiculously large. So we also use a smaller unit for coulombs by just adding metric prefixes in front of the coulomb, right? So we have the micro coulomb, which is 1 times 10 to the negative 6th coulombs, right? Micro is 10 to the negative 6th. We have the nano coulomb, which is 1 times 10 to the negative 9th coulombs. And we have the pico coulomb, which is 1 times 10 to the negative 12th coulombs. These are oftenly used units for electricity. Microcoulomb is typically the most used unit for electricity. We will almost exclusively use microcoulomb for our units when we talk about the amount of charge on an object. So here's an example that has to do with number of electrons in coulombs. If we removed 16 million electrons from a neutrally charged sphere, what is the resulting charge on the sphere in coulombs? So go ahead, take a second, try to figure that one out. I'll take a sip of my coffee here. So you should remember that the electron is negative 1.6 times 10 to the negative 19th coulombs, which means that the amount of charge that we took off of that is equal to the charge per electron multiplied by the number of electrons that we removed. So we had 16 times 10 to the 6th, that's 16 million electrons removed at a charge of negative 1.6 times 10 to the negative 19th coulombs, which resulted in a total charge that was removed of negative 2.56 times 10 to the negative 12th coulombs. Now remember, this is the amount of charge that was removed. So what's left over? The positive version of that. And so the amount of charge on the sphere afterwards is positive 2.56 times 10 to the negative 12th coulombs, or positive 2.56 picocoulombs. 2.56 picocoulombs. Now the benefit of knowing the amount of charge in coulombs of an object is that a lot of work has been done to determine the amount of force in between any two charged objects. And so this is Coulomb's law. Coulomb's law is that the force of attraction or repulsion between 2 point charges is directly proportional to the product of the two charges and inversely proportional to the square of the distance between them. So that concept, that description should sound somewhat familiar. So if we have a positively charged object and a negatively charged object, those two have some charge, Q and Q prime. They exert some force between the two of them based on the green one's charge and the pink one's charge and the radius in between them, right? So the closer we get, the bigger that force is going to be. The bigger the charge is, the bigger the force is going to be. So that means that our force is proportional to Q times Q prime divided by the distance between them squared. Likewise, if we have two similarly charged objects, they will have a repulsive force equal to Q prime over R squared. Now if we take a look at this, this makes sense. If we have one positive charged object and one negative charged object, we have forces that turn out to be negative. Right? Because if we have one positive here and one negative here, the result is a force value that is negative. If we have a positive and a positive, or a negative and a negative, that is a positive and a positive, or a negative and a negative, that means that our force value ends up being positive. So here's a nice helpful piece of information. Anytime your force calculations end up being negative, that means we have an attractive force. That means those two objects are attracting each other. Their forces point toward each other. Anytime we have a positive force, that is two positives or two negatives, our force is repulsive, which means they're pointing away from each other. Now, to actually calculate the electric force, we have to know a proportionality constant. That's the number that comes in front of here, right? Because we said this was proportional to that, but it's not exactly equal to it because there's some proportionality constant. So the proportionality constant depends on our choice of units for charge. So this is where we typically are going to have to use coulombs as our final answer. So when our charge is in coulombs and the distance is in meters and the force is in newtons, we have the resulting equation or the resulting value of our proportionality constant to be 9 times 10 to the ninth. So I know I mentioned that in class last time. 9 times 10 to the ninth is our proportionality constant, which means that if we were to take this equation here, kqq over r squared, we would have k being 9 times 10 to the ninth as our value. And the units for that are Newton meter squared per Coulomb squared. Newton meter squared per Coulomb squared. This is remarkably similar in function. This equation is remarkably similar in function to Newton's law of gravitation. And so let's do a practice problem. If we have a negative 5 microcoulomb charge, placed 2 millimeters from a positive 3 microcoulomb charge, what is the force between the charges? So with electricity, a lot of what's going to help you with these is diagrams. So it is helpful to draw and label the given pieces of information on a diagram. So if we have our negative and our positive, we have those are the charges. Our negative is negative 5 microcoulombs. Our positive is positive 3 microcoulombs. They are 2 millimeters apart. That's our R. And we're asked to find the force F. We know it's going to be an attractive force because it's one positive and one negative. But how much is that force going to be? So go ahead, take a second, try to figure that out, pause the video, come right back. And here we're back. So we're going to use Coulomb's law, kq prime over r squared. And we see that our constant of proportionality there, 9 times 10 to the ninth, comes in front. Negative 5 times 10 to the negative 6, right? Because this is microcoulomb. It's very important you pay attention to the prefixes in front of our units. Microcoulombs here, so we have negative 5 times 10 to the negative 6, 3 times 10 to the negative 6, then our distance is in millimeters, so 10 to the negative 3 meters. So our value, 3.38 times 10 to the negative 4th newtons. Now keep in mind that this will be negative when you calculate this. So you can either express it as a negative force, or you can say it's this value of the force, and it's an attractive force. So the negative sign only determines our force direction. A negative means attraction, a positive means repulsion. So here are some helpful problem-solving strategies for problems like this. So first, as always, you should read the problem, and then this is particularly helpful for these problems where we can't actually see these charges, can't actually see the electrons. You should draw and label a sketch showing all of the appropriate information in SI units, right? And you should you should make sure that you have your understanding of the prefixes, because we're going to be using a lot of prefixes here. Remember, don't confuse the sign of the charge with the sign of the forces. Attraction or repulsion determines the direction of the sign of the force. You can also go in reverse. The sign of the force determines whether it's attraction or repulsion. Remember, a negative force is going to be a force of attraction. A positive force will be a force of repulsion. When we're determining the resultant force, we have to consider the force because of each charge independently. Now, in general, when we're talking about an object or a system of just two objects, we're only going to be talking about the force on one of them, because the force on one of them is the force on both of them from Newton's third law. But if you have a system where there are more than two things that are causing a force, you have to be careful to make sure that you are reviewing the force from each object that's causing a force. You're adding them together. You're calculating them individually and then adding them together. And then you should remember that for forces in equilibrium, we have net force in the y and the x direction both equal to 0. So make sure you copy this down. That's helpful. So let's see a problem that has more than two objects that's working in the problem. So say we have a -6 microcoulomb charge that's placed 4 centimeters from a +9 microcoulomb charge. What is the resultant force on a -5 microcoulomb charge located midway between the first charges? So we have 3 charges. We have one charge, -6, we have another charge, +9, and in the middle we have a -5 microcoulomb charge. And I want to know what's the resultant force on that -5 microcoulomb charge. So first, draw and label your diagram. Here's the diagram. Q1 is what we call the -6 microcoulomb charge, Q2 is the +9, and Q3 is this -5 in the middle here. We know that the distances are 2 centimeters and 2 centimeters because they are 4 centimeters apart, these outside ones. So next is going to be to draw the forces. We have a force from object 1 that's pushing the 5 microcoulomb charge, -5 microcoulomb charge to the right, and we have a force from object 2 that's pulling it to the right. So both of our forces pull to the right. Remember, because we're just asking about the resultant force on the -5 microcoulomb charge, I don't care about the fact that Q1 is pulled to the right from Q2, or that Q2 is pushed to the, or pulled to the left from Q1. I don't even care about the fact that Q2 is pulled to the left from Q3. I just care about the resulting forces on Q3. Next, we know that our resultant force is going to be toward the right, so we're going to call right positive here. And so we have the force between Q1 and Q3, which is 675 newtons. We have the force between Q2 and Q3, which is 1013 newtons. And what do we have to do to those two forces? Well, this is vector addition. We're back to vector addition. Those two forces are pointed in the same direction, so they add together. Right, they add together. So we have a rightward force that's what we're calling positive. So our force 1 is 675, our force 2 is 1013. We have to add those two forces together, and so the result is that our net force is 1690 newtons. That's all I've got for you today. You're going to have a homework quiz on this video tomorrow in class, and we will start to work on practice problems in class having to do with electricity. See you next time.